So the next thing, so the first thing that we actually arrived at is that we have now our maximum likelihood estimator for beta head, and that takes this form. And the first thing I want to do next is to get also the maximum likelihood estimator for sigma square. Yeah, I think I will just do that. It takes completely the same approach. So again, we start with the log likelihood function. One thing that happens here is, and this is how it's typically done, that we now, previously we treated the variance essentially as known, so the variance parameter is known, and now what we are doing is that we substitute our estimator for beta into the log likelihood function, which then looks at as follows. So we have our log likelihood function now as a function of sigma square, as we wrote it up above. And this takes, of course, the same form as we previously have seen for the beta head estimator. It's the same multivariate Gaussian probability density function, of course. And the only difference is that we now put in our beta head estimator here, because we know that now. This approach, however, is also not without problems, because this is this beta head estimator, of course, has some yeah, maybe I dropped the ML. So with the beta head, it's always what I mean by the maximum likelihood estimator. This has some shortcomings in the sense that this is, of course, only an estimate. And now we derive another estimate based on already an estimate. And this actually then later on leads to the fact that the maximum likelihood estimator for sigma square is actually not the best that you can do. And actually what is better is to do what is called restricted maximum likelihood estimation. Nevertheless, I will show you what comes out here, and then you have learned something. And it's a very typical approach, and you see that in the statistical textbooks. So the aim then is to again compute the derivative. And now if we do that, if we now have this log likelihood function and compute the derivative with respect to sigma square, we first see again that this term is not dependent on sigma square, so we get 0 for it. And the first term that we need to compute a derivative with respect to sigma square is actually this. One thing that actually helps in computing the derivative and see things more clearly is if we put this division by, it's just a little help, by sigma square here instead of there. It's just easier to see. So here we have the derivative of log sigma square. Does anyone remember the derivative of log x? It's just something that you either know or you don't know. Somebody feel like they know the derivative of log x? Yeah, exactly. So here we then obtain minus and half 1 over sigma square. This is just a fact that you know or you don't know. Here, well, whether I did it like this or not, but anyway, so here we see that we have a fairly long constant that's a constant, and then we have a number to the a variable to the power of -1. So what is the derivative of x of a function where you have x minus 1? X. Yeah, so minus, that's true. X, that's also true. And square is also true. But what you said is minus x squared. Do you mean this?
No.
1 over, sorry. Yeah, which is to the power of -2. Because you have to subtract 1 here and you have to take the 1 in front. So here we have, so if we do that, then we actually get a plus. And yeah, actually I wrote it here also with 1 over, although I didn't want to do it. So we have this expression, and of course the constant remains. So we have this. It's a very healthy Monday morning with some derivatives and so on. How else would you want to start a week? It's very healthy. So yeah, now we are already where I wanted to get with respect to the derivative. Then of course the approach is again to set to 0. So we have our derivative here, which we now set to 0, which means that we set this expression to 0. So let's see. Maybe we just continue here. I don't have to rewrite things. So we are now here and set this to 0 and want to solve, of course, for sigma square. For sigma square. We might as well then already put our little head here. Then basically we do it as previously. So we put try to isolate our sigma square, and this is now a little bit here I'm using a little bit of tricks, so I will a little bit of a trick, so I will show you what happens. So first put this on the other side. So we're taking this over to the other side, so we have n half 1 sigma square head. What am I doing then? So we can get rid of our division by 2 because we have that on both sides. So we can multiply the whole thing by 2, and we get rid of this, and we can write this. And then, and then we multiply both sides by this, which leads to yx beta t y minus x beta hat sigma square hat. So that was the square times n divided by sigma square hat. Which then we can cancel out one of these sigma squares, so we get sigma square hat times n, and then we are already there, so we can now divide by n and get sigma square hat. It's 1 over n, or maybe I read it the other way, y minus x beta p y minus x beta hat divided by n. And that is already the maximum likelihood estimate for sigma square. There are a couple of interesting things about this. First of all, it's not the one that is actually used for estimating parameters in the GLM, because it turns out that this is a bias estimator. You have seen this problem before. So remember when you computed standard deviations in undergrad statistics, you computed something like you had data points, let's call them yi, and you subtracted your mean and you squared them, and you summed over all of your data points, and then you divided by n, or did you? By what did you divide? When you compute standard deviations or variances in undergrad statistics. Remember that? Do you divide by n or something else?
N minus 1.
Exactly. So it was by n minus 1, and then the question was always why n minus 1. It was not really clarified, and we will also not clarify that here. The reason for that is the backstory for that is if one thinks about the expectation. So if one views, we will come back to that, and we have to come back to that. If one views the estimator as it's the realization of a random variable for which one can compute an expectation because one can sample the data, then if one then compares the expectation of this estimator to the true but unknown value, one sees that these are actually not the same. For the beta estimator, these are the same, which is also known that this is an unbiased estimator, and also more generally, it's actually the best. The beta estimator has the smallest variance in the class of linear estimators. The sigma square estimator doesn't have this property. The sigma square maximum likelihood estimator doesn't have this property. It's a bias estimator. And if one looks at that in more detail, one sees that one can actually easily correct the bias if one does what was done here, namely not divide by the number of data points, but by the number of data points minus 1. You might remember that there was something like the degrees of freedom or the actually effective number of data points, because here if you have the mean, then you all except for one data point are free to vary. This is all the same kind of conglomerate of stories that never really gets really clear. It only gets clear if one actually looks at the mathematical statistics of computing the expectation of these parameters. However, we will not do that here because that's actually mathematical statistics and beyond the scope of this course. I mean, I would love to do it, but we would have to do other things. Because it's actually very interesting to study the properties of estimators, but I have to teach other things also here. So one can correct for it, and the way one corrected here was by subtracting 1. Here one can actually, this was the case when one essentially has one beta parameter. Here one needs to divide by the number of individual beta parameters to the dimensionality of beta. So this means, what this essentially means is that this is the estimator. This is not the maximum likelihood estimator, but it's very close to the maximum likelihood estimator, and it's the estimator that we will actually use all the time. And is kind of a bias corrected version of the maximum likelihood estimator. This means that Yeah, the important thing is that this means that maximum likelihood, although I discuss it here as a general method, and you will also in your other papers that you're looking at for behavioral models and so on, you will always see maximum likelihood estimates. There is no guarantee whatsoever that maximum likelihood estimates and maximum likelihood estimators are actually good estimates. Yeah, so it's just a procedure, and it has some intuitive appeal. And for the better head estimator, it works nicely. It also reproduces the ordinary least squares, as we talk about in a second. But there is no guarantee whatsoever, and you already see that for this estimator. Another thing that is interesting, or I find interesting here, is if you think what you actually have in the numerator, because you might see, I would hope that you see, but maybe you don't see that yet, what is written up here. If you look at the individual components, so if you think that this is an n-dimensional thing, this is an n-dimensional thing, oh, sorry, this is an n-dimensional thing. This is an n-dimensional thing. This is also an n-dimensional thing, as are those. We looked at it previously also from this perspective. Then what you actually compute here is the residual sum of squares. This might be surprising, but it is. If you look at it like this, so your y is a long vector of n with n entries. This is your prediction that you make based on your estimated parameters. So it consists of n. So it's like the expectation parameter. It's also n-dimensional. It's not a matrix or something. It's just a vector, and they are all in this. And so then you have this transpose and multiplied with itself. As I earlier discussed, this is like squaring. So what you actually compute there is the sum of squares, of the residual sum of squares, yi minus x beta hat I, where this means the ith entry of this vector, and you square that. What that means is, if you think about this now in terms of, for example, a simple linear regression fit, is that if you have some data points here, so, and now with the beta head estimator, you found a procedure to find the best fitting line, right? So based on the beta head estimator, you can now compute the slope and the offset of the simple linear regression model. I mean, this is what this allows you to do. I mean, maybe that's not completely clear, but that's of course, amongst many other things, that's one thing it delivers. Yeah, so you can fit the parameters of, for example, a simple linear regression. Then you have this line that shows the fit. And then you still have, even after fitting this line, of course, you have here some remaining error terms. So the line fits the points, but it doesn't fit every single everything, a single aspect of it. So you have these residuals. Yeah, and now if you compute all these residuals which you have here. So this is the observed data. This is your prediction. So this is exactly this difference here. And you compute them, you square them all, and you sum them up. And then, of course, you divide again by the number of parameters. Then this is an estimate for your variance, which I find interesting because it's a little bit surprising, right? So you have, thinking about this, you have some residual error, and this is actually your best estimate on the variance parameter of your error. That's somewhat surprising, at least I found. But that's what comes out for the variance parameter. Yeah. With respect to this, I want to say a little bit more now also for ordinary least square estimation. But yeah, so the things that I was mainly concerned with is this. Other questions about this derivation of the variance parameter estimator? No. Good. So we are actually from in terms of our model, we are now really far in terms of model formulation, model estimation. So maybe let's summarize briefly. So our model is this. Now we can obtain a realization y, let's call that y star for the moment. And now we have formulas to actually do parameter estimation in a frequentist setting. So we can do for this y star realization, we can compute a better estimate because of the hat, and star because it just refers to this data, by using our design matrix, multiplying it, inverting it, and just multiplying it with our data realization. And also we have an estimate for the variance parameter, which we get from taking our data, subtracting our prediction based on our estimate for beta, and dividing by the number of number of data points minus the number of parameters. Yeah? So maybe before I talk about ordinary least squares, let's make sure that you really get what this actually delivers, because and let's say we do that again in terms of our simple linear regression example. So remember, we had simple linear regression. I don't want to do the numbers again, but the concepts. So remember that based on true but unknown parameters, this the GLM made these. It's not the greatest ever, but based on true but unknown parameters, the GLM says for the simple linear regression case, it makes this prediction of a straight line. And then we've seen before that we can sample from that. So let's say we sample now blue data points. Blue or black, I don't know, let's make them black. We sample, maybe we sample data points, and I on purpose make a little bit of a weird sample here. So this would be our y star, which we have sampled, and then we can compute parameter estimates for our true but unknown beta and our sigma square, true but unknown sigma square. And in this case, the true, at least for the beta, this would be where the offset looks almost like 0, and the slope might be something like 1. So this would be true but unknown value, and let's say that our sigma square is 1 or something. Then the estimates would of course also, so the estimates would of course also be for the beta parameter would be a vector, and you see that the data is a little bit funky, so that actually you have these 3 data points up here, which don't follow exactly what the prediction would be, because it would be more that one of these data points also below the curve. So what will happen most likely here is that the estimate will, or the parameter will be a little bit wrong, because the data is a little bit wrong, not representing the underlying thing correctly. Maybe makes that a little bit more extreme and clearer. So maybe like this, so that the slope is a little bit misestimated. So let's say the slope is estimated like this, and the sigma square is estimated, let's say roughly the same. But so this blue point can go away. This is what this whole thing now really delivers, so that you can basically now fit a line. That's the fit. The black thing is the real data, and the red thing is true but unknown. And you see that in this case, because the data is a little bit misrepresentative of the true but unknown issue, also the fit is a little bit off. Yeah? Good. So this is what this whole thing really delivers, but it delivers this not only for the simple linear regression case, but for all things that are in the GLM. So for t-tests, for ANOVAs, for ANCOVAs, for everything. Everything that is in the GLM, we now have parameter estimates. And next time we will look at actually look at this a little bit more abstractly. If we sample more data, what we can actually say about the distribution of these parameters. But the last thing that I want to do today is to relate, I think this will be the last thing actually, to relate this to ordinary least squares estimation. Yeah? Because I assume that who of you has encountered ordinary least squares estimation? Ordinary least squares. Okay, 2 people have encountered ordinary least squares. And I now want to tell you what these two things have in common, at least for the beta estimator. Right? So this was just summary. So now ordinary least squares. So the way, because it's also in the script, the ordinary least squares estimation looks very similar to the maximum likelihood estimation, and in fact the formula for the beta parameters are identical, but there are differences. So ordinary least squares estimation can also be motivated from a simple linear regression example, where you have some data points and you want to fit a line to it. So again, you can write the line in terms of a GLM. So you can write this as your x1, x2, so like we did the simple linear regression GLM previously, and of course you also again need 2 beta parameters to make a line prediction, and then depending on how the beta parameters are, you can come up with different fits. So for example, one fit would be this, one fit would be this, another fit would be this, all sorts of things, but all looked a little bit bad. Now the story about ordinary least squares estimation is that you try to find better parameters that have the probability, not the probability, but have the property that if you look at your yi and you subtract from it, also what we've seen above, the ith prediction of your model, so this GLM here, so your x beta, that you choose your beta parameter in such a way that this, what we also really just some time ago called the residual sum of squares, that this residual sum of squares or ordinary squares is minimized. Yeah. So if you plot this and make this very intuitive, what these residuals of course correspond to is for a given fit, and maybe let's make a bad fit on purpose. So for, let's say, this kind of setting, which of course doesn't fit the data well, these ordinary squares are the summed, like we've seen before, the summed deviation in this direction. Yeah. Of course, it's really large now for this fit. So you try to fiddle with the beta parameters such that these deviations, which are indicated there as these straight lines, that they become small, so that what you actually want is something like this, so that you have on average for your deviations or summed over them a small error. So let's maybe put that a little bit more formal. So your beta ordinary squares wants to be the minimizing argument. So it wants to minimize the sum of squares, the residual sum of squares. Yeah, for the people that have seen ordinary squares, are they happy with what I just said? One person is nodding, the other person is not remembering what actually happened in ordinary squares. So she assumes, she hopes for the best. Okay, so this is the typical logic of ordinary squares estimation, that you say, okay, I want to find a line, or in general more a fit to the data that minimizes, once I have obtained my parameter estimates, minimizes the deviation between my prediction and the data. Yeah? That's the general logic of least squares. It's also a more general logic of kind of predictive estimation techniques. The question is, what comes out? What comes out? I can tell you. There you find a derivation also in the script. What comes out is actually the same thing as we've seen for maximum likelihood estimation. So it comes out to be the same formula. The question is, what is the difference then, or why is that, and why does maximum likelihood, and so why does maximizing the likelihood function in minimizing the ordinary squares, why do they achieve the same thing, and what is the difference? At least that's what I always ask myself when I was young. Then with a little bit of thinking, one actually sees why this is happening. So maybe let's focus first on the differences. OLS versus maximum likelihood estimation, because you will also, and this is very confusing, you will most of the time actually you will read that in the GLM literature, in fMRI, you will always hear that this thing that I just erased, that this thing is the ordinary least squares estimator. This is the ordinary least squares estimator for the beta head parameters, that's true, but in fMRI GLM, we use the whole thing to do inference and to later do evaluate p-values. And there wouldn't be any p-values if there wasn't a probabilistic model, so it would make much more sense to call this either Gauss-Markov, as it's referred to as in the SPM literature, or at least in the SPM book, or the maximum likelihood estimate. Because in ordinary squares, from the logic that I've just shown you here, there is no probabilistic model. Yeah? There are data points, there are parameters, there is a model, but there is no probability. OLS. No probabilistic model. Which means the following: you can always do ordinary least squares estimation whether you formulate a probabilistic model or not. Yeah. Maximum likelihood estimation you can only do if you actually formulate a probabilistic model, because only then you can formulate a likelihood function by defining it as the probability of the data as a function of the parameter, and then do further things with it. But that's a fundamental difference. Yeah. So the ordinary least squares works without probabilistic models. But why then did I tell you that it actually comes to the same, it results in the same? Well, this happens because essentially of this thing and how it looks in what we've looked at previously. So we've seen that an important term in the derivation of the maximum likelihood estimator was this minus x minus 2 sigma square y minus x beta t y minus x beta. And we've also discussed that this is nothing but a G thing. The residual sum of squares. So that the residual sum of squares, which is the error function or the scoring function or the loss function, however you want to call it, of the ordinary squares approach, of course plays a role also in the case of the maximum likelihood estimation. Now, can one say a little bit more? Well, this thing is always larger than 0 because it's a square thing. So it enters the exponential with a negative sign. So if we are looking at the exponential function, we are actually in this part of the exponential function. So we always get something negative. So this is what we are actually looking at. Sorry, there's no minus sign there. There shouldn't be a minus sign. So this is when we still have the thing, I was confused for a second, when we still have the original likelihood function with the 2 pi minus n half sigma square minus n half. So it's this function that I'm talking about, not the likelihood function. I confused myself there a little bit. So likelihood. We want to maximize likelihood. So coming back to this, we want to maximize this with respect to beta. So this thing we cannot maximize with respect to beta because beta is not in there. So we want to maximize essentially this term here, the entire term with respect to beta. Now, we maximize this term. If you think about how the exponential function looks, we maximize this term if we make the argument of the exponential as small as possible. So if we essentially go this way. And we cannot go below 0, so going positive, because we will always have something negative in here. So by maximizing this thing, we are at the same time minimizing this thing. Yeah. Did I confuse you at one point with this? If yes, tell me where. No. So this shows that minimizing the residual sum of squares and maximizing the likelihood in a GLM for the beta parameters is the same thing. Yeah, so it's although you have the one in one approach you're minimizing something, in the other one you're maximizing something, you're doing the same thing. This is why the same thing comes out, but the frameworks that are behind ordinary least squares estimation and maximum likelihood estimations are of course fundamentally different, because in maximum likelihood estimation you base everything on a probabilistic model, whereas in ordinary least squares estimation you just base things on a model and some data, but not a probabilistic model. Yeah? Now this is finally clear to all of you. I know you waited for a long time. Good. I think I want to then stop here. Other questions? No questions? Good. So then next time we look at the distributions of these parameter estimates that we looked at today. See you then.